morning, everyone. It's a pleasure to be here. And thank you to See Clear for sponsoring this wonderful workshop and for inviting me to moderate today's panel. Back in the late 70s, when Love Canal came to the forefront, our technology knowledge for dealing with contaminated sites was quite limited. We were pretty much confined to dig and haul, excavation of contaminated material and hauling it off to a landfill for disposal. And with respect to groundwater, it was pump the water out of the ground, treat it, and discharge it to a nearby water body. So for the past 40 years, we've come up with a number of innovative technologies that are much more sustainable. Now, there's still applications for excavation and disposal when you're dealing with sources of highly contaminated soil. And there's still reasons to pump and treat groundwater. But this morning's panelists are going to talk to you about some of those new sustainable and innovative technologies. For the most part, these new technologies can save you costs on your cleanups, can save time, and can reduce environmental impacts as well as human health impacts, resulting in a more sustainable solution. Our panelists, I'm going to introduce them one at a time here later on, but I just wanted to give you a brief overview of their talks. First, Bill Ottaway from New York State DEC is going to give you an overview of a wide variety of technologies that are well proven at other sites across the state and the country for treating both soil and groundwater, both in the ground, otherwise known as in situ, and above the ground, also known as ex situ. He's going to be followed by Todd Calder from EMSI, who's going to talk about one technology for dealing with organically contaminated soil in an ex situ or above ground environment using thermal treatment. Dan Knoll from LaBelle Associates is then going to give you a presentation regarding the application of chemicals to groundwater in situ to treat chlorinated solvents, one of the most problematic contaminants that we have to deal with. And then finally, Christian Mercurio is going to tie it all together with an innovative approach to a former vacant manufacturing site where beneficial uses were incorporated into the planning and design and implementation of their project. So with that, I'd like you to join me in welcoming Bill Ottaway, Chief of Technology, Support, and Training for New York State DEC.
Okay, and it's good to be back at RIT. The last time I was here was for the annual juggling festival they have every spring. I thought about bringing my torches and decided that was not an indoor activity. As was mentioned, this is going to be an overview. My normal role is to get down into the weeds and talk in a highly technical manner. I'm going to be going through a variety of technologies fairly quickly. Anybody who wants to geek out with me afterwards, I'll be hanging out in the lobby, very happy to do that in more detail. Okay, I'm going to be talking about a number of different technologies. First, I will touch on excavation. There will always be a role for excavation in cleanup of sites. But I also want to talk about some other technologies, bioremediation, in-situ chemical oxidation, soil vapor extraction, and if I have time, I'll do a little bit of talking about thermal treatment. Okay, one of the first things I want to mention is when you're going into a project, you should not presuppose what the solution is going to be. Let the investigation lead you to the right solution. Just because you've had success using one technology in a previous site, if that site was on sand and the new site is in clay, that old technology isn't going to work, and you have to let the investigation lead you to the right solution. When you're selecting those remedies, the first thing that, if you're in one of our programs, we're going to make sure that you're protective of human health and the environment. Once we make sure you've done that, the next thing we're going to be looking at is making sure you're following all the rules, which in a more bureaucratic sense we say is complying with all the applicable standards, criteria, and guidelines. Okay, once you've achieved those two basic things, protection of human health and the environment, and you're following all the rules, we do have a policy to make sure that the cleanups are done as sustainably as possible. If you go online, you can find DER 31, our green remediation policy. We want you to minimize CO2 emissions, minimize the use of resources, and maintain or improve habitat if applicable. We're also looking at climate change resilience. This is particularly true where you're dealing with waterfront properties. Flooding is going to be an ever-increasing problem. You do not want that soil cover that you're putting down to turn into a sediment cover, because it's not going to hold up as water is coming in. So we do want to take potential climate change impacts into consideration. And this is a situation where permanent remedies, getting rid of the contamination rather than trying to leave them in place, can be preferred overall. We have enshrined in regulation a hierarchy of what we're trying to do with sites, with the contamination at a site. Ideally, we want to permanently destroy the contamination. That way, nobody ever has to worry about it ever again. If you can't destroy it, then the next best thing is to remove it from the site, so at least we're not going to worry about it there ever again. If you can't remove the contamination, then what we're trying to do is minimize the risk to human health and the environment. And we'll do that through engineering controls to contain the contamination, or institutional controls to limit the use of the property. And those institutional controls would be the least desirable tool, but we do have that in when we need it. As I said, there will always be a role for excavation. The key is you should be looking at excavation for the most accessible, most heavily contaminated material. That is when it makes the most sense economically and technically. One thing I definitely want to mention as well, if you do have an excavation on a remediation project, and you're going to be leaving contamination in place, very often the material you use to backfill that excavation does not have to be fresh material from a mine. You can use historic fill material from other brownfield sites or from other sources of mildly contaminated soil throughout the community. So this is one of those beneficial uses that we should definitely be keeping our eyes out for as we're moving through the process. Okay, the real focus, one of the focuses of my talk is going to be combining technologies. As I said, we want to let the investigation drive us to use the right technology, and just because we decide that excavation is right for a part of the site doesn't mean that that's the only technology we'll bring to bear on the cleanup. Maybe we'll excavate the shallowest, most heavily contaminated material. We'll use one of those in-situ technologies for the deeper material, something like that. If you are going to excavate some soil, think about what you're doing with it after it leaves the site. If you are disposing of it, contact the landfill. Make sure that it's being used if it can be, as daily cover. At a landfill, they have to cover up the garbage every day. That is one of the uses that you can have for that mildly contaminated soil. And the other option is treatment. Todd's going to be talking about thermal treatment of petroleum contaminated soil and other soil contaminated with other organic material. One of the other things I want to mention that people should keep in mind is a technology called chemical stabilization, and especially for lead contaminated soil. If that lead contamination is heavy enough, then that soil would be characterized as hazardous waste. It would be very expensive to dispose of that material. If you can mix in a chemical to lower the pH and complex the lead with other minerals, then the lead will not leach out of the soil, and you can dispose of that as solid waste at a landfill, regular landfill, instead of having to deal with it as hazardous waste. So that can be a really significant savings, and it can conserve the limited hazardous waste disposal facilities that we have. There are a number of things that make excavation less possible. Buildings, utilities, other obstructions. If you have a particularly nasty site, I used to work at the old manufactured gas plant sites, a lot of times the odors during the excavation would be so strong that you'd need to have a structure with air handling equipment over the excavation. Again, that makes it more expensive. Also, the shoring of the excavations and water can be very expensive and very difficult to deal with. Okay, first alternative technology I want to talk about is in-situ chemical oxidation. And when people think about in-situ treatments, this is usually the first thing that pops in their mind. What we're doing there is we're trying to destroy the chemicals in the ground, the contaminants, with an oxidant. Those oxidants, back in the beginning, were typically peroxide or ozone. And what they do is they break the organic materials down into their constituent materials, H2O, carbon dioxide. When done completely, it breaks it down into those elements. The most common use of the in-situ chemical oxidation is on chlorinated solvents, the dry cleaner sites that were mentioned earlier. One of the keys is that in-situ chemical oxidation works best in the sweet spot where it's a source of a source area where the material you're treating is a source of groundwater contamination, but it's not pure product. It's not what we call non-aqueous phase liquid or NAPL. If you have too heavy a contamination, you're not going to be able to destroy enough of that contamination with the in-situ treatment to make it effective. So you're definitely looking for that in-between sweet spot with the in-situ chemical oxidation. You will find vendors who will say that it's possible to treat those really heavily contaminated sites with in-situ chemical oxidation. It is possible, but from my experience, it's rarely the correct choice. There probably are unique situations where that would be appropriate, but in general, you're looking for that middle ground. And in general, the in-situ chemical oxidation works best below the water table. It's the oxidant gets into solution and breaks the contamination down that way. Last thing I want to mention is you have to have realistic goals for your in-situ chemical oxidation. You probably are not going to meet your groundwater standards after 1 or 2 treatments. There's probably going to be some residual contamination. So very often you're using in-situ chemical oxidation in association with bioremediation, which is going to be my next talk, or next topic. Some areas where in-situ chemical oxidation does not work as well as others, tight soils, which is to say clay. It works in solution, so if the soil is more or less impermeable, it's going to be very hard to get the chemical in contact with contamination. A lot of people talk about in-situ chemical oxidation as a contact sport. You have to get contact between the chemical and the contamination. The other thing is, especially with those earlier chemicals, the ozone and peroxide, you really needed to know exactly where the contamination was. Those chemicals were really short-lived, and within a few feet of the injection point, they would get used up by the the materials that were creating an oxidant demand in the soil. So you really needed to have pinpoint accuracy. Nowadays, peroxide and permanganate are beginning to dominate the industry. If you know exactly where the contamination is, the peroxides are still a good choice. But the permanganate and persulfate options stick around longer. They can be there for as long as a couple months, and they can move into the contaminated area from where you're injecting them. Okay, next topic, as I said, is bioremediation. And In particular, the most common place we use bioremediation is for those chlorinated solvents like the dry cleaners or industrial solvents. And it's a process called reductive dechlorination. Dry cleaning material is tetrachloroethylene or perchloroethylene, and there are actually 4 of these chlorines on the ethene molecule. And what the reductive dechlorination is doing is knocking off one of these chlorines on each step. So TCE is transformed into TCE, transformed into dichloroethylene, transformed into vinyl chloride, all the way down to ethene, which is, as I say, a harmless byproduct. There's a relatively small number of bacteria that are able to do this. In the past, there have been a lot of people trying to spend a lot of money seeding the contamination with the right biology. Our experience so far lately is that basically we're bug farming when we do this technology. We're trying to make a good environment for happy bugs, and as long as you make that environment, the bugs will get there. So you usually don't have to inject the bugs. They'll usually come along on their own, but the key is to make that healthy, happy environment for your bugs. One of the best times to use enhanced bioremediation is where it's already working. From that earlier slide where we were looking at the degradation products, if you do your investigation and you're seeing vinyl chloride, dichloroethene, then you know you've already got reductive dechlorination taking place, and all you want to do is make your bugs happier, get more of them working, and make it work faster. You're probably not going to be attacking the source areas using this technology. It is possible, but we're primarily using this for plume control. So it's if you have a site where for some reason you just cannot get to or cannot completely treat the source of the contamination, this technology will allow you to keep that contamination on your site, control it, and let you continue your development while it stays there under control in the ground. Basically, in-situ bioremediation, you're working with nature as opposed to fighting against it. Generally, the conditions under the water are anaerobic. You usually do not have a lot of oxygen in the groundwater. If you look at your soil, if it's red, that's oxidized iron. If it's gray, that's reduced iron. So below the water table, it's usually gray. You're in a reduced zone. If you're using an oxidant, you have to oxidize all of that iron, all the manganese, a lot of this other inorganic materials before you start treating your contamination. If you're using enhanced bio, you're already working with the existing system. One thing I want to mention, one of the evolving technologies that we're just starting to use this year is carbon injection technology. There are a couple different vendors. But what this is doing is putting an activated carbon in the ground, which would then capture the contaminants and then create a bioactive zone where where the reductive dechlorination would be taking place. And what's the theory is that you'd be able to do the injection and have a clean stop of the contaminant where you're doing the injection, as opposed to having it peter out along the way. We're doing our first injections of that technology this year. Very optimistic that it'll be another good tool in our toolbox.
Could you say what the carbon does when you inject it?
So activated, the question is, what does the carbon do? And if you're treating drinking water and you have PERC, TCE in your water, you can use granular activated carbon to remove that contaminant. And this, the activated carbon in the ground does exactly the same thing. It traps the contaminant within in the activated carbon, and then that gives a very good substrate for the reductive dechlorination to take place. Very often you're using a carbon injection followed up by an injection of one of the enhancements for the biodegradation.
Otherwise, the contamination just sits there to the carbon until it's released again.
Right. And so if you have a contaminant like PFOA, PFOS that does not degrade, you can still use this carbon injection. It'll still stop the contaminant. And they've got a couple case studies where they've been able to protect the water supply using this technology. But it's a Band-Aid. And once it is used up, then you need a second step, a second injection, or something else. I must be running out of time.
Hang on. So if you could please hold your questions until all 4 panelists are done. We've got quite a bit of material to get through.
Okay. You can have biodegradation of non-chlorinated organics. Generally, that's just a matter of adding enough oxygen to keep those bugs happy. One of the new technologies, if you have non-chlorinated organics like a gas station and you have anaerobic conditions, you can improve your biodegradation by adding sulfates and nitrates. So that's another type of biodegradation. Back 10 years ago, we always would throw oxygen-releasing compound in the bottom of the hole just to help a little bit. We're not doing that anymore. It doesn't seem to help very much. But if you have a contractor who's suggesting that, I wouldn't bother. As we're talking about these enhanced bio, you're also going to hear the term monitored natural attenuation. Be careful with this term because that assumes a very structured approach. If you're using monitored natural attenuation, you have to have a goal that you're reaching, and you have a deadline to reach that goal, and then you also need to have a fallback technology that you're going to use if you don't reach that goal. So very often people come in saying, oh, we want to use monitored natural attenuation. What they really mean is we want to use biodegradation, we want to monitor to make sure that it continues working, but we don't have a deadline. So that's something to be careful with. Phytoremediation is very attractive. This is using plants to treat your contamination. Unfortunately, I have seen lots of people trying to use this with relatively little success. White rot fungus was a big buzzword several years ago. It didn't pan out. The reality is that if you're trying to treat the contamination organically, the bacteria generally do a better job than the plants. It's possible that we'll find some plants that'll do a great job somewhere down the road. For right now, the bugs are doing a better job than plants. One exception is that you can get hydraulic control of a very shallow plume with plants. And in that situation, the plants are drawing the contamination up into the plant, releasing it into the air. If you have contaminants that photodegrade well, that would make sense. So there are applications, probably not a very common thing. The last technology I want to talk about is soil vapor extraction. And one of the principal routes of human health exposure that we see, especially with these chlorinated solvents, is soil vapor intrusion. It's vapors getting into the buildings from the vapors that are moving through the soil. If you have a site where you have very high levels of soil vapor extraction is probably going to be one of your preferred technologies. What you're doing is you're putting in sinking wells, putting a vacuum head on that, and drawing the vapors into a treatment train. Back 10 years ago, we were using this. It's an effective technology, but the original use of this was relatively low power and long term. And now we've moved from that approach to a more high power, short term approach. If you're running one of these things for 10 years, that's not very green, it's not very cost effective. What you want to do with your soil vapor extraction is hit it hard, remove as much of that source material as possible in as short a time as possible, and then move on to one of these other technologies, maybe in-situ chemical oxidation, bioremediation.
What is a short amount of time?
6 months or a year it would be the typical goal for this technology. If you're running it for 5 years, that's the time to say, wait a minute, let's take another look at this site, see if another technology would be more appropriate. That having been said, we do have sites where we aren't able to remove that source, and we're using the soil vapor extraction to cut off an exposure pathway, something like that. So there are situations where we do use it for a longer-term solution, but it's generally not cost-effective and not what we're looking for. So I was talking earlier about combining technologies. And if you have a shallow source of contamination, which is where you have gross contamination and it's accessible, excavation is still a very viable technology. In this situation, you could also use a dual phase extraction, which is basically that soil vapor extraction I was talking about before, with liquid extraction added in. So that would be another technology you could use in that source area. Above the groundwater table, soil vapor extraction, or you could just continue your excavation into this other area if that ends up being cheaper. Down below the groundwater table, excavation gets very expensive because you have to deal with contaminated water. So that's when these in-situ remedies come in to really play a stronger role. You can use the chemical oxidation. One thing you can do along with soil vapor extraction, if you bubble air into the contaminated groundwater below the water table, that can draw the contaminants into the vapor phase, and you can capture that with your soil vapor extraction system. That's called air sparge. So you'll often hear people talking about an air sparge SVE alternative. And then with the less contaminated area, that is where your bioremediation really shines as a strength. I'll just mention one more thing, which is in-situ thermal, where excavation is not practical, and especially where you have tight soils, clay. In-situ thermal treatment is becoming a viable technology. It's been around for 10, 15 years. In the past, it was too expensive. They're bringing the costs down. If you have heavy contamination in clay soils, this really has become a viable technology. If I had lots of time, I'd fly through a bunch more slides. With that, I'm going to move on.
Good. Okay. All right, thank you, Bill. Our next presenter is Todd Calder, Vice President of Sales for ESMI, and he's going to be talking about ex-situ thermal treatment. Please welcome Todd to the stage.
I'd like to thank Gene and the Center for Creative Land Recycling for having me here today. Bill kind of set the bar very high for everyone on our panel today, so you did an awesome job. So today I'd like to talk a little bit about thermal treatment as a choice to consider for contaminated soil. And in the room, how many people have heard of thermal treatment for contaminated soils? Just raise a hand. All right. How many people in the room have actually sent soil to a thermal treatment facility anywhere in the Northeast? All right. So this is talking about, is thermal treatment a smart remedial action for your project that you're working on? And what are the benefits for thermal treatment? During the presentation, I'm going to talk a little bit about landfill locations throughout the United States. I'm going to talk about the process of loading out soils from a site, bringing it to a thermal treatment facility, what the process is, and the true beneficial reuse of thermal treatment. This is a slide in 1966. This is the green dots are closed landfills, and the red dots are open landfills. Now, I put this slide up here because that's about the time that I was born, maybe a couple years before that. But anyway, that's what the United States looked like with landfills. Now, if we fast forward to 2017, this is what it looks like now. which is absolutely incredible. My wife and I have 5 kids, and we talk about their future and their kids' future. And that, with that number of landfills that are going on, is kind of concerning, actually. So let's talk about a project that you have. And if you plan on excavating a site because you want to clean the site up and you want to get it off the DEC list and you want to be able to transfer the property and you want to not have any more liability going forward, you would excavate the site. And here's a particular site with a truck being loaded. Here's another particular project. This is coal tar. Now, thermal treatment has a lot of advantages. Thermal treatment can treat coal tar material, which is this, PCB soils, chlorinated solvents, which is what Bill talked about a little bit from dry cleaners and laundromats, besides gasolines and fuel oils and waste oils. But that's typically what a coal tar site will look like after it's excavated. So now I just want to kind of go through what the overview of a thermal treatment process is. So once that material gets excavated, it gets loaded onto a truck, and it gets sent to a thermal treatment facility. This happens to be a facility in New York, up in Fort Edward. And it doesn't look like what you would see as a normal thermal treatment facility, but this is a thermal facility. In the background is the storage building of the facility. So that truck, that's a dump trailer truck, and in the state of New York, you can haul 35 to 38 tons per load. And if you've ever seen one of those trucks with the dump up, it's pretty impressive. Sending those trucks to a landfill, because of how high that goes, if that ground isn't totally level and totally solid, there are more of those trailers that flip over on the side. And that's why it's always good to have a nice, freshly paved, level lot, so you don't have that problem. So once the material is offloaded into a thermal facility, into the building, basically the loader will take the material, and depending on the contaminant, will put it in different bins. So if it's gasoline, it goes in a certain bin. If it's coal tar, it goes into another certain bin. And the reason for that is because the different properties of the contaminants, in order to successfully treat them, you have to have certain levels. So gasoline, we may treat at 550 degrees. Coal tar, we'd have to treat at 975 degrees. So depending on the contaminant will determine what the temperature needs to be successfully treated. So you'll see in the storage building there are different piles, and those different piles represent what the different contaminants are. In the process of a facility, what happens is that everything gets screened down and then crushed, because it has to be treated. So when we're receiving material that's 8-inch or 10-inch, we have to actually crush that down to 2-inch minus so that we can ensure successful treatment. So after it's screened, then it's crushed, and then it's fed into a unit. And you can see it's actually coming out just before a screen deck. And what you'll see is that flight right there is the material that was loaded inside the building coming out, and anything that's over 2 inches gets dropped down into that screen deck right there. So it's screened a second time just prior to treatment. The control room, the gentleman that operates the unit, or the people that operate the unit, basically have to monitor all the controls and make sure that the temperature is at the right temperature for the soils that are going in. And sometimes if the contaminant is too contaminated, what will happen is it increases the temperature in the kiln. So that has to be adjusted. Now if you look at that, that's basically a 45-foot barrel that revolves. And inside that barrel are flights, and those flights actually turn the contaminated media inside, and it's also has bricks as a kind of like an insulator from the heat escaping out there. But that basically will turn, and the residence time that the material is in the drum is approximately 10 minutes at the temperature that it needs to be based on the contaminant level. There's a lot of emissions equipment on thermal units, and you just have to. So sometimes what you'll see when it's colder in the fall, in the wintertime, you'll think it's smoke coming out of the stack, when in fact it's just steam coming out of the stack. We just did a PCB test about 2 years ago, and we treated it down to 5 nines, which is almost unheard of. Typically, you hear of 3 to 4 nines treating down to, but we went down to 5 nines. Now, this is the material coming off the conveyor after it's treated. And what you're going to notice is that thermal treatment actually changes the color of the material. It actually darkens it a little bit. But you'll see that it's all sized down to 2" minus. There's another pile on what it looks like. Now, the true beneficial reuse of thermal treatment, if you're a facility that treats the soil to actually clean up standards, is that you can actually sell this material to contractors, to anyone. This particular picture up here is the Loudon Country Club. We treated 320,000 tons of soils over the course of several years, and actually supplied that Loudon Country Club with all material to make that country club. So thermal treatment basically will eliminate your liability. It won't extend your liability if you send it to a landfill. It will not, like in situ, could last for years and years and years, but actually cleans up the material, eliminates the liability, and truly can be used for beneficial reuse. And you're not using the Earth's natural resources from mining other material, because this material can sometimes be shipped back to the site of origin. We do that quite a bit as well. So anyway, with that, thank you very, very much. Appreciate that.
While we're waiting for this to work, I'm going to mention, with the dry cleaning sites, if you have PERC or TCE in that soil, the PERC and TCE is a listed waste. So any amount of PERC and TCE in that soil could characterize your soil as a hazardous waste. Hazardous wastes are a lot more expensive to deal with. If you have just a little bit of that contamination, you can contact DEC and they can do a contained-in determination to say that as long as you're below a certain level, that soil can then be handled as a solid waste and not a hazardous waste. So that's definitely something to be aware of, this contained-in determination. And if you're sending it for thermal treatment, the level at which you can issue a contained-in determination is much higher, because the thermal treatment is going to be effectively destroying that contamination. So that's definitely something I want everybody to be aware of in terms of saving money on these dry cleaner sites and ideally destroying that contamination instead of just disposing of it.
Thank you, Bill. And thanks to Todd, and my apologies for the technical issues. Next presenter is Dan Knoll. He's a project manager at Labella Associates. He's going to talk about in-situ chemical treatment of chlorinated solvents. Dan?
So I've got a case study that I want to present on in-situ chemical treatment. I actually have, for this site, and some of you know it, I think there's probably at least 10 or 12 people that have worked on this site over the years in this audience today, so many of you will recognize it. But we actually have 2 treatment areas that we had. There's many area concerns. I'll kind of briefly review those, but we use both in-situ chemox and in-situ chemical reduction at this site. I'm really just going to probably focus on the chemical reduction because on my dry run, I really didn't have enough time to get through both. So the site's here in Rochester, New York, probably 15 minutes up the road here on the northern side of the city of Rochester. It's in the DEC Brownfield cleanup program. We've been working on it for a number of years, a little bit longer than our developer client would like, but we've been working through it. The main contaminants I'm going to talk about, as mentioned before, are chlorinated solvents, TCE, and its degradation products. So it's a little bit washed out here, it looks, but you can kind of see the shaded areas are where we did dig and haul. So these are interremedial measures that we completed over the years to address different areas of the site. It's a little hard to see, but the purple area is petroleum. Some of that maybe we could have sent to Todd, but it actually went to a landfill. But some of these were done very quickly before some occupancies of the building happened. So 2 of the areas I'm going to focus on are what we call Area Concern 1, and that's an area solvent. And you can kind of see, hopefully, on the top part of in that circle is kind of a turquoise area that we did in IRM, and I'll focus on that in a second. And then Area Concern 8, if we have time, is where we did the in-situ chemox. So this is Area Concern 1. Kind of off to the right there is the extent of the removal we did, if you can make that out. Hopefully on the next slide it shows up a little bit better. But that's what the dig looked like. You can see that there's NAPL or free petroleum product floating on top of the groundwater, and that was our source area that we wanted to attack and remove as what I would consider a surgical removal. It's a little bit, and I'll show you in a second on the next couple of slides, we're kind of hemmed in by buildings here. Dig and haul really isn't an option anyways, not as though we would do it, and some of the contamination, most of the contamination is down in the bedrock, so we wouldn't be digging that out anyways. I'd have you kind of look at the slide and see that we've got a pipe sticking up out of there, a steel pipe. That's our bedrock well 5. That well in particular, in that NAPL, we had about 2,400 parts per million of TCE, which is an extremely high concentration. It represents a continuing source to groundwater that would be there for decades. So we wanted to do the surgical removal and remove that. As we did this, you can kind of see in the slide, hopefully, that we ran into rock, and we actually removed rock to try to attack that NAPL because the NAPL was trapped in the layers of the bedrock, and we wanted to get that source out of there. We didn't want to have to deal with that for years, so we could look at other technologies like in-situ, which I'll get into in a minute. So after the IRM, we had addressed soil for this area. The DEC cleanup standard for protection of groundwater and unrestricted use for TCE is about 0.47 parts per million, and we met that through our removal. We really were just left with the groundwater. Groundwater in this area is down below the top of rock, about a foot or so into rock. Seasonally, it fluctuates above it sometimes, so we will get some overburden water, but for the most part, it's bedrock water. After the removal, I had mentioned we had that 2,400 parts per million in the NAPL, in the actual oil. Beneath the NAPL, we had dissolved concentrations of TCE at about 120 parts per million. After the removal, we were down to our highest concentrations of 6,200 parts per billion. So we saw huge decreases. That's not even the hottest well that we had before, bedrock well 5 that I mentioned. That one went down to about 3,000 parts per million for TCE, or sorry, parts per billion. The other thing, and Bill mentioned this, is, and I'll get into it a little bit more, is we really wanted to and looked at the fact that we had 30 to 80% degradation products. So TCE, as Bill mentioned, goes down to DCE, then vinyl chloride, then ethane and ethene. We were seeing the dichloroethylene and vinyl chloride at about 30 to 80% of the total volatiles in the wells we were sampling. So we already knew we had degradation occurring, and we wanted to spur that on with the in-situ chemical reduction, which I'll get into. So there, that shows up a little bit better, luckily. The brown area, the dashed line, that represents our removal of soil. I've got on the next couple slides, we show the areas of rock that we removed, but that was our highest well. You can see the little call out to that in the middle is our bedrock well 5, which we had about 3,000 parts per billion after the removal. You'll kind of see, and it gets washed out there, but that 1,500 part per billion line, that's total volatiles. What I show in the call-outs are the TCE numbers, so you can see that our total volatiles, especially when you get over towards bedrock well 6, is a little hard to see, but that's that 6,200 parts per billion. The total volatiles were closer to 9,500 parts per billion. So that one we had a bit more TCE, but the other wells, you can see that some of the concentrations are 160 parts per billion, but we're probably at like 2,000 total volatiles. So we've got a substantial degradation occurring. So the things that we considered during the design is we looked at, we basically have bedrock groundwater impacts that we have to address, not really overburden. We have that significant degradation that I mentioned. So we looked at what I would call M&A testing or monotonical attenuation testing, although we weren't looking at non-monotonical attenuation as the remedy. But we do similar testing to make sure that we understand that things are reducing. We have the degradation products, but we want to look to make sure that we, have the conditions right and that we think that it's going to work by spurring it on with enhanced bio and in this case, zero valent iron. So things we look at are like dissolved oxygen. We want that to be less than 1, so we have those anaerobic conditions. We look at the oxidation reduction potential. We want that more like minus 100 to minus 50 millivolts. In this case, we were down to about a minus 145, and these are average concentrations within the plume. So we would look at upgrading of the plume, in the plume, and downgrading of the plume to see how the geochemistry is changing throughout the groundwater. Other things that we looked at were ethane and ethene. Those are the products that Bill mentioned that everything reduces down to that, which are really kind of more, I guess I would say, inert or compounds that we're not so concerned about. Now, we did see relatively low concentrations, but it is showing that we're getting full degradation, not stalling out at dichloroethylene or vinyl chloride, which can be a concern. So we looked at other things as well, like you can look at iron, iron 2, sulfates, nitrates, nitrites, those types of things. Look at where you're at in that degradation product or process and what's the limiting factor. So for this one, as Bill mentioned before, we kind of looked at Chemox initially, but knew that that would maybe have some nice short, quick approach that the developer would like, but we also knew that we're down in the bedrock, we're going to have long-term release that I'll get into in a minute as well. But we wanted to use that naturally occurring degradation that we're already seeing and take advantage of that rather than try to switch the process into something that may seem quicker but maybe doesn't really work in the long run. So we settled in on Ferrox Plus, which is a Hepure Technologies product that is, they call it the Ferrox Plus, which is zero valent iron enhanced bio. So this is a little bit more of a zoomed in look to see what our remediation looked like. So we have that black dashed line, kind of funny shape up there, that's where we actually ripped the rock out. And I didn't mention it before, but we wanted to go with injection here. And as we were ripping the rock out back during the remedial phase, we wanted to take advantage of what we already had open and not limit ourselves and not be able to go back to that area easily and right to the right spot. So we put in some infrastructure, which is just very simply some perforated horizontal piping that we put in a pea stone bedding and ran some riser pipe up to give us an access point to either remove from later or inject into later. In this case, we did injection into it. The kind of hexagonal dots throughout that show in kind of a line are where we did injection wells. Now those are bedrock wells that we installed down into the rock to give us a place to inject into. So we ended up with 12 of those, and then we also, as kind of a way to pull across the site, which you can see here is our extraction wells. Some of these don't show up too well, but we have extraction wells where we wanted to inject on one side of the site and try to draw it over with the extraction wells with a little pump and treat system. The real intent wasn't to operate that long term and make this a pump and treat remedy, but to pull across our injection chemical to make sure we get distribution across the formation. So that is the arrow showing here, and you can't really see it, but I had put in there some little halos around the injection points that show what is our conceptual radius of influence, and then we would draw that across the site. Now I show a cross section here because one thing, this cuts from the building side down towards the street, which is on the bottom here, and that is one of the concerns is off-site impacts and things extending off-site for this project. So we had to address that, and this cross section goes from left to right towards the street. And so as we did the work, we learned a lot. We had 4 or 5 data points throughout the formation in the rock, and that gave us a good indication of where things were, but as we did the project, we learned a lot more. So we started doing these wells into the bedrock and found that we had a pretty significant fracture. I'll probably mess this up and the geologist will hit me later, but we had what I would consider a mud seam. About 6 feet into rock, we saw a pretty good amount of mud or soils that were in that fracture, and enough where we could actually sample it, get a 4-ounce jar and analyze it at the lab. And with our PID out in the field, we started seeing some spikes at that location, and we started honing in on that because we weren't expecting those types of concentrations. So once we submitted this to the lab, we started getting 100 parts per million in the soil down in that mud seam. So we also started looking at right above and below that seam, the rock, the actual rock matrix, to see what has diffused into the rock and what's going to be a problem for, this developer's children and his children. And what we found was that there is some high concentrations in the rock within and around that seam. However, and you can kind of see it here on the extraction well 2, that we've got like 3 or 4 call-outs there, that the TCE in the rock really dropped off as we got a couple feet away from that seam. So the concentrations we felt were pretty localized to that seam, and not above or below it by much. So we feel that there is hope for this site yet, that we can get there eventually. Down in the bottom left-hand corner, that's an actual downhole well camera that we used for one of the extraction wells that we put in. And that kind of shows the fracture. It's a little bit washed out, but you can see that's a pretty significant fracture where we had that mud seam. So we went back to not back to the drawing board, I'd say, but we rethought the approach. We learn something new every day and never have enough data type of thing. But we went back and decided that, we kind of overshot the mark. We had installed treatment wells that went below where we really needed to treat. They would still catch it, but how much of that product are we going to waste on fractures below that aren't going to really help us in the long run? So we actually went back and grouted in the treatment wells a bit and brought them up to about an elevation just a couple feet below where that main seam was that we wanted to focus our remedial efforts on. So how did we do? Well, I think we did all right, although this slide doesn't show it too well. Bedrock well 5, our worst case one, we had that 120 parts per million, or 120,000 parts per billion. We've dropped it right before the excavation with the IRM work down to about 1,000. Since the injection, we've gotten it down to about a half a part per million. So it came down about 55%. And if you kind of go around there, we have some wells that are dropping off pretty good. Now this is total VOCs. Then we have kind of our problem child. As we did the work, a couple of the wells, Bedrock well 20 in particular, wasn't there. We installed that as part of the remedy. And that well kind of surprised us. We had some very high concentrations in that well, 33 parts per million of total volatiles. And that actually went up a little bit with the injection work, so with total volatiles. And then Bedrock well 4, which is down gradient of our apparent source, actually came up as well. But as we mine into the data a little bit further, this is TCE. So as Bill mentioned before, we've got that degradation process from TCE to DCE to vinyl chloride. So this is a marathon. This isn't a sprint at this site because of back diffusion out of the rock. We are really closely looking at what is the TCE concentration doing. And we've had good success. And in Bedrock well 5 in particular, we've dropped that from 120 parts per million to non-detect over the course of just a few years. And over the last 13 or 16 months that we've been monitoring the injection work, which was back last June, we've come down 99%, basically to non-detect. And all the other wells have dropped, including Bedrock well 20, which was a good sign because it was such a high concentration of 21,000 parts per million of TCE. We're down to about 3.6 parts per million. So while we still have to go on with monitoring, we feel that we're in a good position to get this site towards a good place where we're treating it as it comes out of the rock. That's the Chemox one, but I'm out of time.
Thank you, Dan. Okay. Our next presenter is Christian Mercurio. He's the Vice President of Planning and Development for Mohawk Valley Edge, and he's going to talk about a case study where he's pulled together a variety of beneficial uses to repurpose a former manufacturing site and return it to productive use in Rome.
Morning, thank you. Thanks, Mike. Bill, Todd, and Dan. I'll never look at impacted soil the same way again. So what do we do now? Once we've done all of this, what do we do now? This is what we're going to talk about, some of the methods, practices, alternatives, hopefully you'll consider for your toolbox. Most of them proven, some of them not. So I'm glad to see that my former director and mentor and good friend Diane is here because this was a team effort. And before we start this, I want to, Diane and I established some guiding principles before we got into the full construction project. Number one was eliminate blight, right? That's what we're all here for. So reverse disinvestment, create positive value. There was this kind of like fatalism, right? In Rust Belt communities that had taken root, and our primary objective was to break that cycle, break that wheel. So that's what we went into this doing. We can have nice things, right? We can. So enhanced environmental quality. This is a big deal for most of us. I think Norman nailed it when he said that we're doing this not for us, but for the next generation, our kids. So that's what's happening here. We wanted to implement sustainable solutions. We knew that we had one shot at this, so we wanted to do it right, and we wanted to avail ourselves of the technology and practices that were available at the time. So, we wanted to increase, just like Bill said, whenever you can improve or preserve wildlife habitat, we needed to kind of look at ourselves as part of the ecosystem rather than lords over it. It's about time we kind of brought ourselves down to earth. So this was a big principle for us. And finally, activate the waterfront. We have a responsibility to protect the water quality, but we also have a responsibility to create better habitat for us, humans, not just wildlife. We are our favorite megafauna. So we need to treat the habitat appropriately. A species' ability to thrive is directly dependent on the quality and diversity of the habitat, and we need to treat ourselves that way too. So this is, and if anything, if we learn anything from the Amazon, massacre of the past couple weeks, is that place really matters. So we have one shot to make a really great place. These were the principles that went into this. So here we are, Rome, New York. The beginning of the Erie Canal, Clinton's Folly. This was 200 years ago this year. So we feel like we have this responsibility to do the right thing on the canal. And with everything in Rome and most in Rochester and most canal communities that grew up in the Industrial Revolution, we're at the intersection of downtown and waterfront when we're talking about Brownfield. So all these things have to be taken into consideration. All right, so here we are. The story begins at General Cable. This was a massive manufacturing complex, still a Fortune 500 company, employs thousands of people. It employed thousands of people in Rome until it was shuttered in the 1970s. So this area in the dashed red circles where we're kind of concentrating on today. The usual suspects as far as environmental contamination, we had, storage tank, oil sump, storm drains. This is where we really could have used you guys as far as the petroleum impacted soil and many thousands of gallons of contaminated groundwater that we had to deal with. It's pretty standard controls, institutional and engineering. This will come into play later because there's some philosophical issues we kind of had to address employing the practices that we're about to talk about. So we wouldn't be here without the Department of State's LWRP, that's Local Water Revitalization, and BOA programs. Community engagement and community planning is the only path forward on projects that occupy this type of geography. So we owe the entire project to the Department of State and the DEC working hand in hand with us. And the EPA, of course, Phil. This was actually the cover photo of the 2001 EPA Brownfield pilot brochure, for good reason. And this is the site we're working on. How do we get from there to there? Lofty goals. This was a 2009 vision, mind you, right? So this was a long time ago. This was, this is old. This project is older than both of my children. So first, we're going to talk about repurposing material. We rubblized. We didn't know that was a word. We feel like we made this word up. We rubblized 1 million cubic feet of concrete over 6 acres. That's a lot of concrete. This was 95% impervious. So 95% of the site was covered in concrete. All the storm drains collected the water, were infiltrated by filthy water in the subsurface and straight piped right into the canal. So we're talking about improving this resource, the canal. We're talking about making a public space. And our objective was to eliminate the contamination and kind of improve the water quality for the canal, thereby wildlife habitat and our own. It was almost overwhelming. Every time we peeled up a piece of concrete, either we sank into the muck, or we found a new oil sump or plume or impacted soils. And we had to deal with this. We were happy to because we're trying to heal the earth here, right? So we're trying to help the land heal. So we're glad to do that. But it was tough going. Imagine the, I don't know, there's a lot of engineers in here, right? So there's the swell factor of concrete. So 6 acres of concrete turns into 10 acres of concrete all of a sudden. And it was kind of tough to deal with it on site because we didn't want to move it off site. The DEC were there with us every step of the way, and it was just easier to keep it on site. Easier for the world, not for us, right? So that's 32 million pounds, I think, of concrete that we touched over the course of this project. And that's what it looked like after revitalization. So we went into this with looking at like an 8-inch minus spec on the revitalization. We ended up with a 4-inch, which was nice. It was actually really nice for construction. It all locked together really well. But the nature of the machinery, I mean, these were like, diamond encrusted carbide teeth that were crushing this stuff. These are $10,000 teeth, on a multi-million-dollar piece of equipment. We were breaking them daily, not really our problem, it was a contractor's problem, but we tried to share the burden. But it was a struggle to do it, but we're glad we did because, again, 1 million cubic feet of fill is hard to come by, and we produced it all ourselves. So again, here's the site pre-construction, 100% impervious, rail sidings, basements, tunnels, sumps, everything you would see on a former manufacturing site on the canal. This is, probably a 2015 view from Google Earth, but what we did basically was eliminate 85% of the pervious surface. The only things that are pervious here are the driving lanes, all the parking, all the the swales, bioretention, native trees and riparian habitat, all those are pervious. So we literally eliminated post-construction runoff. It was at 95% of all the water that hit that site, and we eliminated it by, if you're looking at these numbers, we got it down to 0. Huge success in terms of green infrastructure. That was like the heady days of green infrastructure with, Matt Driscoll, Susanna Randall. They put this amazing team together and they trusted us on this, and it worked beyond all expectations. We were pretty psyched about it. So peak discharge was 0. Here we found this little gem on the water. Welcome to Rome if you're on a boat, right? So Diane and I had visited Pittsford, Shane Place at one point, and saw we could make a connection here. So what we did was we turned that, instead of underwater excavation, we kept the foundation, turned that into a fishing platform, and connected it by trail to another park. So we connected to the Erie Canalway Trail, we connected it to another 3 acres, we extended the park by another 3 acres along the canal, and it's 100% accessible. So that was just kind of like, there is ways to repurpose some of these horrible structures. This was fortunate. I'm going to go through this other than to say that 5 mayors, 6 planning directors, 19 years, 8 grants later is how this project got done. Every team brought something new to the table. Every team elevated the level of quality, the level of sustainable practices. The current team is killing it right now. They're making it better than we ever envisioned. So again, we went from this to this, all with a lot of help. One last kind of remark, I guess, is I don't know, nature does it best, right? If we're going to help the land heal, let's try to return to natural systems. Nature's figured it out a long time ago. Let's try to return to those processes and, improve habitat for everybody. I think that's it.
Okay, great. Thank you, Christy.